Welcome, everyone, and thank you for being here today. I'm Gina Henry, and I'm the Associate Dean for Advancement for the College of Engineering. In July, the College of Engineering kicked off a new webinar series titled Faculty Insights, a 20-minute briefing. Today's webinar is the fourth session in this series, in which faculty from across the College of Engineering share insights into their research, its impact, and provides perspective for us for the future. Following today's 20-minute presentation, you will have an opportunity to direct your questions and comments to today's speakers. You'll notice that there's a Q&A button at the bottom of your screen, and that's where we would like for you to place your questions. Today, we're delighted to be joined not only by our featured speaker, Liz Holm, but also by Beth Dickey, who is the Teddy and Wilton Hawkins Distinguished Professor and our new department head of Materials Science and Engineering. Beth joined the College of Engineering in January of this year. Prior to joining Carnegie Mellon, she was a distinguished professor and associate head of the Department of Materials Science and Engineering at North Carolina State University, where she also directed the Center for Dielectrics and Piezoelectrics. Her research aims to develop processing structure-property relationships for materials in which the macroscopic physical properties are governed by point defects, grain boundaries, or internal interfaces. Beth has over 150 peer-reviewed journal publications, which have been cited over 20,000 times. Early in her career, she received the Presidential Early Career Award for Scientists and Engineers for her work on metal-ceramic interfaces. She was also awarded the Fullrath Award by the American Ceramic Society in recognition of her research on the characterization of functional ceramics and composites. Beth is a fellow of the American Ceramic Society, the Microscopy Society of America, and AAAS. She is currently an editor of the Journal of the American Ceramic Society. She's editor-in-chief of Cambridge University Press's Elements in Microscopy and Microanalysis, and is currently the president-elect of the American Ceramic Society. She received a BS in Materials Engineering from the University of Kentucky in 1992 and a PhD in Materials Science and Engineering from Northwestern University in 1997. We're thrilled to have her with us here at CMU. I'd like to ask Beth to say just a few words before we begin Liz's presentation today. But before I turn things over to Beth and Liz, just a reminder to please submit any questions that you might have via the Q&A feature at the bottom of your screen, and our speakers will respond to them at the conclusion of this presentation. Beth, I'll turn it over to you.
Thank you, Gina. And I'd like to welcome everybody today and thank you for joining us for this really unique opportunity and celebration of Engineering Week. This is the beginning of my second month at Carnegie Mellon. It's been a fantastic transition for me to be now part of this really great university. Right now, we're in the middle of our spring semester, which the alumni out there, we do have our students safely on campus for some of their classes, and most importantly, the hands-on laboratory that they are engaged in as part of their education. Of course, our graduate students are continuing to pursue their research in these fairly challenging environments, but I think we have figured out a way to work and educate effectively in this environment, and importantly, in a safe way. So all is well here at Carnegie Mellon. I'm grateful to be part of this organization. And again, I want to thank you for participating in today's seminar that will be given by Professor Liz Holm, and for participating hopefully in the other activities that are going on this week and through the weekend. So it is my distinct pleasure to have the opportunity to introduce my esteemed colleague, Professor Elizabeth Holm. Liz has been at Carnegie Mellon since 2012. Before that, she had a very successful career at Sandia National Laboratory, where she spent approximately 20 years there. And we were very fortunate to be able to recruit her to Carnegie Mellon. She has a very unique educational background, and I think you'll see this puts her at a very special and unique position within our discipline to really bring together more traditional material sciences with advances in computation, machine learning, and artificial intelligence, and is really putting us on the map as an institution. She's been a strong leader in that research area internationally. So Liz got her bachelor's degree from the University of Michigan in material science and engineering. She then went to MIT, where she got a master's degree. And then she returned to the University of Michigan, where she was involved in a dual PhD program between material science and engineering and scientific computing. And that really set the stage for the remarkable work that she's doing now. She's been very engaged in the professional societies that are important to our community, including ASM, where she is a fellow of that professional organization. She's also a fellow of the Metals and Materials Society, also known as TMS, and she served as president of that organization in 2003. At Carnegie Mellon, she's not only one of our most outstanding faculty members in terms of research, but also in terms of teaching and mentoring. She really epitomizes, I think, what it means to be an academic researcher that's engaged in research, education, mentoring, and outreach. I hope that you will enjoy her seminar today. One of the other things that I'd like to point out in terms of scientific leadership, she is also responsible for a $7.5 million program that Carnegie Mellon has with the Air Force Research Laboratory that is aimed at bringing together manufacturing with artificial intelligence to really help with the production and development of important aerospace materials, but also very importantly to train the next generation of students who will be future leaders in these areas. So I'm delighted to introduce Liz, and I invite her to take over the stage now.
Hi, everybody. Thank you, Beth, for that very gracious and humbling introduction. I hope I can live up to a fraction of it today for all of you. I'm going to share my slides now and give them a moment to get started up. It is really so many things about our challenges this year have been challenging, have not been fun for us, for our students. But one of the things that has been delightful has been the ease with which we now are able to make connections across distances, across the country, around the world. And so I welcome all of you from everywhere that you're joining us today. And I'm pleased to have you in this virtual conference room together to talk a little bit about advanced manufacturing and what's happening in that area and how materials matter to it. I should mention before I go on, though, that this work has been supported in my group by a wide variety of interested sponsors that you can see arrayed along the bottom of this slide. And it's also work that pervades CIT. And so throughout this talk, I will mention research that's done in other groups that collaborate together to bring together this expertise that's really unique and special for CMU. So this is something that is a CIT-wide effort. And I also would be remiss if I didn't acknowledge my wonderful graduate students, who of course are the people who actually do this work while pursuing their education, and then they go out in the world and become alums, such as many of you here today. And so I'm just so grateful to have such a great group. So I'm going to talk today about materials for advanced manufacturing, and specifically the advanced manufacturing that I'm going to talk about is what's often called 3D printing, or what we call in the engineering world additive manufacturing. That is this idea of taking material and adding it to build up a part in a new way compared to the old subtractive or deformative ways of manufacturing, where we'd either machine away material or deform material into a shape. Now we actually put the material exactly where we want it and only where we want it. That's very exciting. We'll see examples as we go. But before we do, I want to do a thought experiment with all of you, just to get us all on the same page about the importance of material and how it's processed. So here's two piles of potato chips. I think we can all recognize them as potato chips. They are the same size, the same shape. They have that saddle shape, the same golden color. They look crunchy and delicious. Let's think about these two piles of potato chips. The pile on the left, it turns out, is Lay's potato chips, the #1 selling potato chip in the country right now. And Lay's potato chips, as their bag shows, they make their potato chips by taking their raw materials, which is a potato, slicing it thin, and deep frying it in oil, and they salt it. You have a Lay's potato chip. 3 ingredients: potatoes, oil, and salt. The potato chips on the right, they're a little bit different, but still familiar, I think. These are Pringles potato chips, the famous potato chips that come in a canister. Pringles potato chips also have 3 ingredients: potatoes, oil, and salt. But they're made quite a different way. We make potato chips, we make Pringles potato chips by creating a dough out of the potato and oil mixture and pressing it through a die into perfectly uniform ovals, and then baking these into the Pringles form. And any of you who've eaten Lay's potato chips and Pringles potato chips realize something important, which is that though we have the same design here, it's a potato chip, and we have the same 3 ingredients, that's the same materials, we end up with a different product. It has different performance. These two products crunch differently, don't they? They break differently, they feel different, they have a different mouth feel. And so the materials are not the only important thing. It's how we process the materials, and that can give us very different outcomes. So now, let's take our thought experiment farther. I want you to imagine that you're an official of the Federal Aviation Administration. You are responsible for the safety of airplanes in the sky. And someone brings to you from some, say, small manufacturing company here in the US, they bring to you a piece of material, like the one on the lower right. It's an Airbus A380 spoiler actuator valve block. It is a piece from a large commercial aircraft. And they say, I made this part using additive manufacturing, 3D printing. And it's made of exactly the same titanium alloy that the original equipment part shown on the left is made from. And it's made with the same design. It fits in, just plug and play, fits right into the Airbus 380. I even did something awesome. I was able, because of using additive manufacturing, I was able to remove some extra material that I couldn't have removed from the original machined component. So it's actually lighter. So here we've got the exact same part in the exact same material. It's even a little bit better. Do you accept it? Do you say, yeah, great, plug it into an Airbus A380 and fly it out from Denver International Airport? Probably not, right? Because the question you have is the same one we have about potato chips. Yes, it's the same design. And yes, it used the same ingredients, the same titanium alloy. But does it have the same performance? How can we tell? And that, in a nutshell, is the key to these new manufacturing processes, to additive manufacturing being used in industrial setting, is how are we going to accept these parts that are made so differently, but meant to do the same thing as a traditional part? How are we going to make sure that our components, the things we make, are going to do what we promise them to do? And remember, these are parts that are very often in very important applications, such as aerospace or medical applications where we can't accept a failure. Well, that's the question of this talk. Let's talk about how we would do that traditionally, nowadays, if my slides decide. We engineers often talk about how we test to make sure something will work, will perform like we think it will, as make it and break it, destructive testing. And it looks something like this. I make up a bunch of components made out of the material that's been processed appropriately for the part that I'm considering. In this case, what I show here are a bunch of tensile test bars. And then I put them in some sort of test fixture, and in this case, pull on them till they stretch and ultimately break. And I measure the properties, in this case, the stress versus strain properties. This tells me how strong my material is. And I do this a lot. Here are hundreds of broken tensile test specimens because I need good statistics, right? I need to be sure that I can have confidence in the material as it's been made and performs. So that's the make it and break it paradigm. But there's a problem when we try to apply that to additive manufacturing, and that is AM is targeting low volume and high value added and custom parts. For example, this hip joint shown on the left, this is custom made to fit a particular person's anatomy. You make one of them. Down at the bottom right is a specialized part for motor race, for car racing, motorsports. Again, you're making it one or two or three of them maybe for a particular vehicle. Up in the upper right is using additive manufacturing actually to repair broken parts. This is something that the military is particularly interested in because you could bring your factory with you into the field of battle and you could put things back together again with additive manufacturing. But again, you're going to do this for one at a time for things that break. And so when we're making one thing or a few things, it doesn't make any sense at all to break hundreds of samples to test the performance of one part. So how are we going to get there? How are we going to get to a place where we're confident that this hip joint will last for years in a very difficult environment, the corrosive environment of the human body, without having to have an overhead in terms of testing that's prohibitive, that loses us all the advantage of using additive manufacturing? Well, that's something a lot of engineers think about. That's something we focus about a lot at CIT in the additive manufacturing groups that span our many departments. And I'm going to show you a few ideas for how we make progress in that direction. But first, let's look at the additive manufacturing process in action to get some ideas about the ways we might be able to understand it well enough in order to qualify the parts that we make with it. So here's a video. You should hear sound as well. I hope you do. And the additive manufacturing process, in this case, we're talking about metal additive manufacturing using a powder bed process. The raw material is a powder made of metal. You can think of sand or flour, right? It's a powder like that. And we have a bed of that powder. And then you see a bright spot. That's a laser beam, a high power laser beam. And it goes through and it hits the metal exactly where we want it to and melts the particles of powder together to create a solid part. You can see it going through there. Once it does a layer, we sweep more powder across, a new layer of powder, and start again with the laser. Now let's look at what you're seeing in this video. You see the spot of laser light and you notice it's not a uniform spot, right? It's getting brighter and less bright. That's telling us something about the power that's being input into our powder. Let's watch the recoater blade come back, sweep more powder. And then we'll watch the laser again and you'll notice some other finer things. You'll notice some smoke-like stuff coming off. That's telling us something about evaporation of the material and maybe impurities and oxides. You'll also notice if you look very closely that you can see little sparks coming out from around the laser spot. That has to do with splatter of the powder particles and of powder particles that are actually being shot off by the laser. So there's, oh, and wait, listen. You can hear the process going on, and it's not uniform either. You're getting an audio signal as well. And all of this is data, is information about the process, right? So we know something about the materials that are being used, but we're also getting information about light, about sound, about power usage, mechanical resistance to that recoater blade, temperature, humidity, shape. The scan pattern is something we know. There's just this huge amount of stuff we know, of information, of data surrounding this process. Can we use that in order to understand what we're building? And that's the goal of a number of our efforts in additive manufacturing here at CMU. So let me show you how it might work just with 3 quick examples, case studies if you like. We're going to use artificial intelligence. And I always say AI is one of those terms that really doesn't have a good definition, right? Because it means what people want it to mean regarding what they want to talk about. I'm going to use it here to mean the use of complex deep learning tools to deal with large multidimensional data streams, because that's really what AI is. In a sense, all AI is really good, really high dimensional statistics. It's the ability to take data far too complex to analyze by hand and find the trends in it, find the commonalities and use them. So we're going to use AI on this huge data stream that we have surrounding additive manufacturing. And we're going to do that in order to support the human goals for the additive manufacturing process. The specific tools that I'm going to talk about today, briefly, are data science, which is this idea of aggregating data in a useful way, computer vision, which is the ability to use computers to look at things in a visual manner and make judgments, and machine learning, which is another way of saying optimizing. It's a way of figuring out the trends and ideas that are captured in the data in order to use them to learn things. And we're going to use them across the whole additive manufacturing stream, which starts with the raw material, that powder metal. It goes through the process control. You just watch the process happen. We have to know about all that data going on there. And then at the far end, it looks at the quality of the product that is produced. It looks for things like defects and flaws and so on in this heat transfer device. So let's start with the raw materials. Our old way of looking at something like a powder material looks like this. I have, say, in this case, some electron micrographs of the powder material. All those white blobs you see there, those are powder particles. Those would look, if you had them in your hand right now, it'd look like you had some sort of grayish, soft sand, and it would feel smooth, almost like talc. But what you would really have are individual particles of metal, and here they show up in these pictures. And we would measure these individual particles of metal, and we'd turn them into a graph. And the graph would be a graph of particle sizes. This is just the particle size distribution. It's a histogram. And you'll notice that we've turned what is rather complex and interesting data, because look at these particles, they have all different shapes and sizes, and they've stuck together, some of them, and they have protuberances and stuff, and we've turned them into a simple graph. We've lost a lot of information in this process. Is there a better way? Can we use our new tools, our tools for dealing with complex data, to come up with a better representation for our raw materials, one that might be more amenable to understanding their properties and how they work? So here's the new way. Start with the same pictures, but now I let my computer vision system extract from these pictures every single individual powder particle. And then I ask the computer to do something that I would never ask a graduate student to do, which is I say, can you sort these, please? So I may have thousands or tens of thousands of particles. I think there's about 10,000 in this particular data set that I'm showing you. And the computer is able to use what's called unsupervised machine learning to figure out natural clusters of these particles. And they're clustering naturally on how they look. And I'm purposely putting quotes around that. How they look has a lot of information in it. It has size, it has shape, it has surface relief and roughness, it has degree of agglomeration, and so on. So what we've asked the computer to do is understand each of these particles as an image and sort those images into visually similar groups, cluster them. And when we do, in this case, we asked for, can you make 8 clusters of particles? And you'll see that when we plot out all these image patches, we find that they group together by visual similarity, and we can see what these groups correspond to. For instance, the watermelon colored cluster, cluster number 1, is particles that have a lot of melt splat all over them. They have surfaces that have had melted metal adhered to them. Group number 7, which is the purple set, they are elongated and weird shaped particles. Group number 5, the magenta set over on the left-hand side of our cluster plot, they're the nice, smooth, round, spherical particles. So you see what we've been able to ask the computer to do is to come up with a much richer, more comprehensive way of characterizing our powder material. And now we can do statistics on this. I can tell you exactly what fraction of my powder is made up of those beautiful number 5 particles, which are the kind we'd really like for smooth spreading and easy flow of the powder in the additive manufacturing machine. And we can start to tie, for example, the number of type 0 particles, the agglomerates that get in the way of flow, with the properties of the particle in the machine that make it harder for the machine to create a nice smooth powder bed. And so now we have a way, using computer vision and machine learning, to characterize our powder in a way that helps us be better engineers, helps us engineer a better additive manufacturing process. So let's move on to the process itself. How might we monitor the process? We just together watched a few cycles of the additive manufacturing process. So we did what humans do, peer inside the box and watch the build go on and hope that they catch problems before they develop into something that's not fixable. For instance, literally, graduate students sometimes stand and watch their build and turn it off if it starts to go bad. Well, that's not an effective way to do things in an industrial setting. So how might we approach the build process itself in the new way? And this, I might mention, is work out of Jack Buth's group in mechanical engineering. There's also significant work in Bharat Kara's group and other groups in the civil and mechanical engineering departments in this area, as well as significant work in Professor Tony Rollett's group in understanding the power regimes in which we can operate the additive manufacturing machines. I'll show a simple example, and this is from Jack Buth's group, of aggregating that data. Remember that huge set of data that happens in the build process? Well, we can start with data simply on the picture of the powder bed, which we saw with our own eyes. And on top of it, we might add the design of the part that we're trying to build. We have that information. We have a solid model for the part. So we superpose that with what we know of the machine. We can also do, during the process itself, autonomous defect identification. This is, again, using computer vision. So here we're actually showing during the build, all the colors here are highlighting states of the powder bed in the system, whether they're good or bad, and if they're bad, in what way are they bad? Are they, for instance, a streak left behind by the recoater blade, or are they a hillock that has been created sort of like on a dirt road when the blade goes over? And then we stack those layers up to get an image of the part that we just built, color coded to tell us whether it's what parts are good and what parts may have problems. And we can then compare to what we actually built. And in this case, you'll see that we saw pink problem areas on this turbine, on this fan blade, right where the build failed on the actual build. And so this is a way to aggregate some layers of data in order to understand what happened in a build. And if you can understand what happened in a build, you can also start to predict what will happen in the next build and make predictions for how to build things with the appropriate densities, tolerances, and all these other things we need to do to make sure it's a good build. I will say, this example is rather simplistic. It used a lot of visual information, but we're adding into that audio information. That is from the sound of the build. We're adding in additional information about the appearance of the laser spot during the build, and so on, adding more and more and more data to get better and better and better predictions and control over this process. It's an exciting area. Now, once we have a part, well then, we have to make sure it's a good one. And again, we're not going to take 100 different samples and break them. We're going to have to figure out how to tell if it's a good part in some way that is less destructive, at least, and is also less intensive in a labor sense. Now, right now, what happens very typically in industry is that a human looks at the part. In this case, looking at the microscopic substructure of a sample of the part, a portion of the part, in order to see what kind of defects and flaws that there are. And this is a tedious process. It literally is someone with a microscope looking over this whole entire piece that I show here. And so they might look in this area and they see, well, that looks like they magnify, oh, it looks pretty good. Move over here. Yeah, this area looks good. When we get over here, we see something that looks iffy. And now we have to delve into it and see what it is. Is this an actual defect? Is it a piece of dust on the surface? What is it? And if it is a defect, what is it going to do to the performance of the material? This is a standard way of proof testing batches of material produced by traditional manufacturing methods. It doesn't scale very well when we talk about going to additive systems. And so we're looking for ways to do this in an autonomous manner, a manner where we can use this idea of artificial intelligence, computer intelligence to do this tedious job. And so here we've trained a computer vision system to recognize a good structure, the desired structure shown here on the slide. And with that in place, the computer can scan through and find all those regions of the sample that are good, that meet specifications. And it's quite robust with respect to things like brightness and contrast variance and so on. And it can also flag any parts that don't look like the desired structure. And you'll see here that these areas of the material have very different looks one from another, but they all look different from the desired structure. And it turns out that 2 out of 3 of these are considered bad outcomes, but the middle one is actually just fine. It's just different. So we haven't eliminated the human from this, but she can now look at just the defective or substandard or different structures, decide which ones need further attention and which ones don't, save a lot of time and get us a lot closer to being able to do an extremely thorough job of understanding the substructure of our built components. So I'm going to finish up with just a few observations. We want to make things out of the same ingredients we've always used, but in new ways, using 3D printing, additive manufacturing. And we can use artificial intelligence to capitalize on this incredibly rich set of data that additive manufacturing brings us in order to optimize the raw materials of the process, in order to control the process, and to qualify the outcome, the product. And I'll finish by saying CMU is an international leader in this area, in the research and the development of AM. The Next Manufacturing Consortium, an industry and government consortium with 12 members, is our linchpin. It is cross-cutting across CIT, and it interfaces as well with 2 large additive manufacturing centers that we have, a NASA University Leadership Initiative in developing qualification of additive manufacturing processes, and a large Army Research Lab center, a $25 million center on AI for additive manufacturing as it impacts the Army's mission. So I'll stop there and hand the gavel back, as it were, to the moderators. I thank you for your attention and look forward to questions.
Thank you, Beth. That was a great present. Thank you, Beth and Liz, both of you. Liz, that was a great presentation. I have to confess that now I'm wondering if I have any potato chips in my house. So thank you for that as well. Just a reminder to all of our attendees, if you have any questions, to pop those into the Q&A box. We do have one that has just come up for Liz and or Beth. Liz, I think this is directed mainly at you. The person says that this is a super interesting topic, and it's sort of a 2-part question. Can you share what is the typical volume of training data set required for the machine learning model to learn to produce reliable predictions? And does your AI system accumulate knowledge over time, benefit from lifelong learning, or is failure analysis and prediction unique to each manufactured part?
Hi, Jeff. Those are great questions. As in terms of the volume of the data that is required, we're used to thinking of AI as requiring these giant data sets, right? Like Facebook's, facial image recognition they have over 1 billion, they get, I believe, over 1 billion images uploaded to Facebook a month, as I recall currently. So they have these huge data sets to learn from. one of the fascinating things we've learned in pursuing this area is that that's not always required. We can sometimes get really impressive results with rather small data sets in computer vision. And this is probably not the forum to go into the details of why that is, but very briefly, we find that if we take the right kind of image, it's a rich information source. An image of of a person probably just has 1 or 2 or 3 people in it. An image of the substructure of a material has a lot of features in it that all have to do with the behavior of the material. And so we're often able to get very good results with surprisingly small data sets. That said, more data is essentially always better data when you're doing data science. The more data you have, the more you can learn from it. So without a doubt, our goal is always, I don't know if lifelong learning is the right word when you're talking about an AI, but certainly continuing to learn, continuing to aggregate knowledge as more information is available is the absolute goal of this. And all the more so in AM, we would like to learn about the hip joints properties, having learned something about the airplane parts properties. We want to make sure that we capitalize on all the information we've gotten in the past, even as we move on to new products and new places. Yeah.
Thanks, Liz. So we have another question that came in from Aaron. Are any types of additive manufacturing competitive with machining for high tolerance applications?
Yes, so additive has the ability, and I should say that there are different AM modes, different ways of depositing the material and so on, and different ones have different tolerances, obviously. But there are additive manufacturing processes for metals that are able to obtain both high pitch, very low pitch, small pitch, and high tolerance. That said, so we can do some very complex parts with some very, very fine features that are reproduced well. That said, there's no question that there are some issues. One is that we use a powder, and you're going to have a surface finish that is going to be related to your powder size. So you're not going to get perfectly smooth surfaces without some post-treatment. So surface finish is an issue. That's an issue. And in addition, there can be stresses, residual stresses due to the process, and those have to be dealt with somehow, usually by annealing. We also have the potential for porosity, often dealt with by hot isostatic pressing. So there are some post-treatments that can get you to a really good high tolerance finish part.
Thank you. Questions are coming in. Thanks to the audience for submitting such great questions. Next one on the list is from Tamara. What are your choices of powder?
So most powder bed additive manufacturing uses gas atomized powders of whatever metallurgical alloy you would like. We collaborate with some folks at Ames Lab. They've been doing powder metals of rarefied alloys for decades for powder metal processing, and now all of a sudden there's a new market. But I would say probably the most common powder that gets used in these applications, 6 lumen, 4 vanadium, Ti-6-4, a common aerospace and medical alloy. Nonetheless, we can do irons and steels and aluminums and Inconel and nickel-based alloys and so on. It all depends on what kind of powder you have. I will just make a pitch for the wonderful work being done in Professor Tony Rollett's group and by a student we co-advise, Srijana Urasi, who investigates in detail the properties of these powders. And one of the intriguing things is we found that although gas atomized powders are industry standard, we can get very good build results with HDH powders, hydride dehydrated powders, a chemically made powder that's much less beautiful looking, but turns out to work quite well in the machine despite that. So that may be a cost-cutting way to get to a better powder solution. The powder is an expensive raw material for these processes. It is a cost factor for additive.
Thanks. This next question might be for Beth and or Liz, but either one of you can sort of chime in. Or both of you. So this question comes to us from Paul, who says that seems like materials science is becoming less chemistry/thermo and more non-destructive testing/AI. How is the curriculum changing to address this?
I've been talking a lot. Beth, do you want to start this one?
Well, maybe I'll address it first by saying Professor Holm teaches our thermo class for undergraduates. So
Thermo's not dead.
no, it is not. It is a challenge, I think, because we have to be, I would say, more efficient and in the educational programs that we offer our students. Because they have to actually learn more. They still need to know about thermodynamics and creep and fatigue, many of the kind of classical topical areas that are important to our discipline, but they also are now needing to have computer science and machine learning as part of their toolbox as well. So it's something we are continually refining our curricula to make it more efficient and effective. And it's not just in our department, it's really across the college. The other thing I'll mention too is we do, I think, innovation in the curriculum, and Professor Holm was largely responsible for a new master's program that we developed specifically in computational material science and engineering. So I think things that we do in the graduate level, we have room to be creative and give people additional skill sets, even if it's part of a continuing education program. So it's an important problem. We don't leave behind those fundamental core things. They remain fundamental and always will, but we have to bring in these other advances into our curriculum.
I agree. And I will say, never write off thermodynamics. Think about what's happening in the additive machine. You've got energy transfer in both mechanical and thermal energy. It's a thermodynamic process. You have phase transformations happening both on the heating and cooling. It's all phase transformations. We still study those. And as far as fatigue goes, the fatigue of additively manufactured components is a main theme of the Air Force Center of Excellence that I direct. So none of these things are off the table. We've just added some new stuff. So there is a challenge to our students to know where to, to make sure we give them all the tools they need, but we're not getting rid of the old tools.
So Liz and Beth, I do realize that we're a little bit over time, but this topic is so popular. The questions are just buzzing in. So are you both okay to continue for a couple more minutes and answer a few more?
I'm good to continue indeed.
Okay, good. So, and to our audience, if you do need to drop off, we are recording this session and we'll be sending out the recording after the fact. Okay, so next question is from June. Do you utilize simulation for the process optimization?
Absolutely. Let me put it this way. Additive manufacturing, if we want to be metallurgists about it, it's just micro welding. And we have developed over the years really exceptional simulation tools for the processes involved in a welding type process, which is, of course, melting, solidification, joining, surface tension, flow, and so on. And so simulation is an important adjunct to understanding how the additive manufacturing process works. And we use both commercial codes and in-house codes to do so, as do some other major groups in the country. I believe Lawrence Livermore National Lab and Oak Ridge National Lab both have really spectacular finite element-based flow models for additive manufacturing, just as one example, and there are others. So simulation is definitely important here.
Great. Switching gears a little bit, a question came in from Tiffany asking, what are you and your students most excited about for the future of this research area?
I was excited about that question, Tiffany, because I saw it coming up and I thought that's a great question to ask in this context, especially. And I don't know if you're inspiring me to go back and ask my students this question, because I'm going to speculate about it, but I'm curious about whether I'll get it right. So, what I am most excited about is seeing how we can use all the information and knowledge that is there for us in ways that make our jobs better, that make everything better, right? That make the processes better and more economical and more sustainable and make our parts more reliable and everything else. So I'm excited about this aggregation of data idea. But I suspect that my students would go deeper than that. I think that they're excited about being able to have an impact on the world around us. You know, they're excited by the additive manufacturing process, by its possibilities from a sustainability point of view, by its possibilities of enabling products that help people, especially in the medical arena, in the energy arena. I think that they're excited about the idea of being able to manufacture and produce things more locally and in more to a custom level. And my students also seem to really be excited to be working in what's considered a very cutting edge and in-demand area, which is artificial intelligence and machine learning. So that's my best guess, but I'm going to ask them. I do know that they're just very invested and very enthusiastic, and I'm going to find out what their key drivers are. So thank you for that, Tiffany.
That's great. It's always great to go back to the students and hear what they're excited about. Okay, so next question is whether you still require the basic tension, compression, shear strength, and performance characteristics of the finished product. And that question came to us from John.
Oh yeah, you know, we're still designing and building to do something, and that something is going to require bearing a load, for example. Yeah, we got to have all of that. Our goal is here to be able to predict those properties based on how we build the part, instead of having to always measure them all the time. And if we can get to the point where we say, if we build the part this way, we'll achieve this set of properties, victory is declared. That is our ultimate goal. But it's always working towards the properties.
Great. Our next question comes to us from Aaron, who asks if, are you only working with powders, or are you also working with advanced manufacturing builds from wire?
The bulk of our efforts are in powder bed because we have some really nice facilities in powder bed, but we are getting a wire feed, a high-end wire feed machine in. I don't know the details as well as Professor Tony Rowlett or Professor Jack Buth, or more importantly, Sandra DeVincent-Wolf, the executive director of the Next Manufacturing Center, would. So if you are interested in knowing about the capabilities we have, Aaron, please do email. I would suggest Sandra DeVincent-Wolf with the Next Manufacturing Consortium, and she will send you the info.
Next question is whether the new way can 100% substitute the old way, make it and break it. And that question comes to us from Eileen.
So Eileen, you asked an easy question. No. So not yet, and probably not ever, if I'm being really honest. I don't want to ride on the airplane that's never had a physical test of its parts. You know, that's I'm not there yet. But you may know that in automobiles, crash tests, we all know crash test dummies, right? You know, when they drive in the wall, we've all seen the videos. Nowadays, there are approved numerical simulations of automotive crash tests that the National Highway Traffic Safety Administration permits in lieu of a physical crash test. It doesn't mean that zero tests are done on automobiles and automotive components, but a significant, large, expensive test mode no longer has to be done in the physical world. It can be done by computer. I think that we can go in that direction somewhat. I don't think we'll ever not do physical experiments, not even close. But we may eliminate some of the ones that are either too hard to do, too expensive to do, or too environmentally unfriendly to do.
So it looks like we have time for about one more question. And then for anybody who submitted questions that we've not had a chance to answer, we'll try to follow up in email with some additional information on some of those. But thanks to everyone for all the great questions coming in. So we will wrap up with this last question from Thomas. Can you explore time correlations in the data collected during your monitoring of the metal advanced manufacturing process? It seems that a defect forming at a location is likely to generate more defects during the next laser sweep. Do you think it's possible to train a network to identify defects that are likely to compound into more defects versus those that will be isolated events?
So Thomas, it's good to see you here. Welcome, and good question. And another question that I could likely answer, yes. We want to do exactly that. And you saw in the example I showed you when we built up the layers that when you start with a defect, you can't build a good part on top of a void, for example, right? And so defects do tend to propagate. Not all defects, as you point out. Some of them do, some of them don't. And very much a part of the process control based on both acoustic and vision-based methods is understanding what defects are going to propagate. And that's step one. Yeah, identify defects that are the kind that are bad for the growing part. And step two is, now could we actually go back and fix them before we move on to the next layer? And that is an active and really important part of this process control effort. Good, excellent question. Thank you all.
Great. Well, thank you, Liz, so much for a very thought-provoking and informative program. And thank you, Beth, for joining us today. And welcome to CMU, Beth. I'd like to thank our audience and everybody who's online with us today for participating. I hope you'll be able to join us at our future Faculty Insights program. And please keep an eye out for an email that will follow up with you soon. And that'll include the recording link to this session. But thank you again so much to both of our presenters and to everyone for joining us. And I hope everyone has a wonderful rest of your day.
Thank you very much, everyone.